In this program, we're going to discover some properties and formulas of several trigonometric functions, and the device we're going to use is that sines and cosines of angles are related to rotations. So let's start by reminding ourselves of the link between rotations and trigonometry. We define cosine and sine using a circle of radius 1 sent to the origin. We take a point 1, 0 on the circumference of the circle, and we rotate it through an angle theta. Then we define the cosine of the angle theta as the x-coordinate of that point, and the sine as the y-coordinate. Now, that's all very well for a definition, but it would also be useful to have a graph of sine theta. And this definition gives us a nice geometric interpretation of sine theta. Sine theta is just this height. So we want to plot this height against theta. But we always measure angles in radians, and the radian measure of an angle is defined as the arc length divided by the radius. But here the radius is just 1. So the radian measure of theta here is just this arc length. So this height and this arc length are all we need to plot sine theta against theta. Since we've got a circle of radius 1, for an angle of theta radians, the length of this arc is just theta. We are plotting theta along the horizontal axis of our graph. Vertically, we plot sine theta, and sine theta is the y-coordinate of the point on the circle. So we've got one point on our graph. For different angles theta, we plot other points, and in this way we can draw the graph for sine theta. Once round the circle, and that gives theta from 0 to 2 pi. A second revolution gives 2 pi to 4 pi. We could continue going round for greater values of theta and plot sine theta for all positive values of theta. To plot the graph for negative theta, we just rotate the point the opposite way round the circle. And so we plot sine theta for all values of theta. So this is the graph of sine, and we found it by using this y-coordinate of the point. If we use the x-coordinate, then we get the graph of cosine. So let's just see what the graph of cosine looks like. Plotting cosine theta is similar to sine theta. Again, the angle is given by the arc length. But this time, we plot the x-coordinate. That's this horizontal length. It's this length that we plot against theta. So by plotting the x-coordinate, we draw the graph of cosine theta. We go anti-clockwise for positive values of theta and clockwise for negative values.
So now we've produced the graphs of sine and cosine, and in fact they look quite similar. Here are the two graphs. They're the same shape, but one's shifted sideways a bit. if you take the graph of sine and move it sideways by pi over 2, then you get the graph of cosine. Now we can use our definition of sine and cosine to explain why the graphs are the same shape. If we take this point and rotate it through pi over 2, we get this point. Well, what are the coordinates of this rotated point? We can get that point from 1, 0 by first rotating through theta and then by pi over 2, or alternatively by rotating first by pi over 2 and then through theta. So the coordinates of this point must be the cosine and sine of this angle. That's to say, they are cosine pi over 2 plus theta, sine pi over 2 plus theta. Now, this point is simply pi over 2 round from cos theta sine theta. So how are its coordinates related to cos theta and sine theta? Well, the y-coordinate of the rotated point is sine pi over 2 plus theta. But that's the vertical height. But that's the same as the x-coordinate of the original point. And that's just cosine theta. So, in fact, we know that the sine of pi over 2 plus theta is equal to the cosine of theta. Well, we can do the same thing for the other coordinate. The x-coordinate of the rotated point, well, it's negative, and it's the horizontal length. But it's the same as this height, and that's the y-coordinate of the original point. So, the cosine of pi over 2 plus theta is equal to minus sine theta. Now, this formula tells us that the sine of pi over 2 plus theta is the same as the cosine of theta. And that's why the graphs of sine and cosine are the same shape, but shifted along by pi over 2. You can see that the sine of pi over 2 plus theta is just this height, and that, in fact, is the same as the cosine of theta. Now, these formulas give us the sine and cosine of the sum of the two angles pi over 2 and theta. And that's a special case of what we're going to do next in the program. We'll find formulas for the sine and cosine of the sum of any two angles. And to do that, we'll use the idea of two successive rotations.
So here's what we're going to do next in the program. We're going to find formulas for cos of alpha plus beta and sine of alpha plus beta. But what do we know? Well, if we rotate 1, 0 through an angle alpha plus beta, then the coordinates of this point are just cos alpha plus beta and sine alpha plus beta, which is what we're after. But we can think of a rotation through alpha plus beta as made up of two parts. Firstly, a rotation through alpha, which is followed by a rotation through beta. Now, that simple idea of two successive rotations is the key to finding formulas for cos alpha plus beta and sine alpha plus beta. When we rotate 1, 0 through alpha, we get to here, and then when we rotate this point through beta, the point moves on to where we want it. And that will give us different expressions for the coordinates of this point. We're looking for the coordinates of this point. We can get to this point by doing two rotations through angles alpha, then beta. This is an alternative way to get to the point. The rotation r alpha moves 1, 0 and the rotation r beta will move cos alpha sine alpha to the point we want. So it's the result of this mapping that we want to find. So we have two alternative ways of getting 1, 0 to this point. The first way is to rotate straight through alpha plus beta, or we can rotate through alpha first, which takes this point to here, and then rotate this point through beta. We can look at it like this. We can rotate 1, 0 straight through alpha plus beta to get cos alpha plus beta, sine alpha plus beta. Or we can rotate 1, 0 through alpha, and that'll give us cos alpha sine alpha, and then rotate this point through beta. Now, if we knew what coordinates r beta sent this point to, then we'd have an alternative form for the coordinates of this point. And it's this alternative form which will give us the formulas we want. Now, we know what a rotation does to 1, 0, but what does it do to these coordinates? Well, to tackle this problem, we'll have to find out what a general rotation through an angle theta does to a general point, xy.
What we want to know is what a rotation r theta does to a point xy. So graphically, we take a point xy and we rotate it through an angle theta, and what we want are the coordinates of this point. Well, what do we know? We know that r theta maps 1, 0 to cos theta sine theta. Well, how can we make use of this? Well, 1, 0, it's on the x-axis. And perhaps we should look at other points on the x-axis. Well, the point we're dealing with is the point xy, and that's related to the point x0 on the x-axis, and also to the point 0y on the y-axis. Now, if we rotate through theta, then all the points x0, 0y, and xy get rotated through theta. So what we're going to do is to look at this rectangle and find out what happens to its corners when it's rotated. To rotate xy through an angle theta, we rotate the whole rectangle through theta. Now we want the coordinates of this point. We can work up to them by finding the coordinates of the other corners of the rectangle. We'll find this corner first. It comes from x0 rotated through theta. Now 1, 0 rotated through theta ends up at cos theta sine theta. If we dilate by a factor of x, 1, 0 transforms into x0, and cos theta sine theta transforms into x cos theta x sine theta. So the point x0 rotated through theta ends up at x cos theta x sine theta. Now the opposite corner. This point comes from 0y rotated through theta. But there's another way of getting to this point. Start from y0 on the horizontal axis and rotate through pi over 2 plus theta. This is similar to what we've just done for x0. So the coordinates at this point are y times cos of the angle we rotated through. That's pi over 2 plus theta. And y times the sine of pi over 2 plus theta. Now we know cos pi over 2 plus theta equals minus sine theta, and sine pi over 2 plus theta equals the cosine of theta. Now from these 2 points, we'll find the coordinates of the point we want. So we have a rectangle with one corner at the origin, and we know the coordinates of these 2 corners. We want to use this information to find the coordinates of the unknown point. Well, we could use a geometric construction that you'll find in the unit, but there's another and a more general way of finding these coordinates, and it uses another transformation you've come across before, translation. Now, these coordinates can be found by finding the translation that moves the origin out to this point. And this translation we can do in 2 parts. Firstly, this translation, let's call it T1, and that takes the origin out to x cos theta, x sine theta. And secondly, this translation, T2, and that takes x cos theta, x sine theta, out to the point that we want. Well, what do we know about this translation, T2? It's the translation that takes the origin out to the point minus y sine theta, y cos theta. Now, to find the image of a general point under the translation T2, we'll have to add minus y sine theta to its first coordinate and y cos theta to its second coordinate. So, for the point uv, it gets mapped to u minus y sine theta, v plus y cos theta. But for the point we're interested in, we'll have to replace u and v by these values. And then we see that T2 maps it to x cos theta minus y sine theta, x sine theta plus y cos theta. And these are the coordinates of the point that we want. So we've completed the general problem we set out to solve. We started with xy, we rotated it through theta, and the point we ended up with had these coordinates. Now, Norman, that's the general formula that you need to complete your problem.
Remember that what I want is a result of r beta applied to the point cos alpha sine alpha. And Bob's given us the general result for a rotation r theta. All I've got to do is to make the right substitutions. Bob's told us where a rotation r theta maps the point xy, but we want the result of a rotation through beta, acting on the point cos alpha sine alpha. So we've got to replace theta by beta, and instead of x we want cos alpha, and instead of y, sine alpha. Making these substitutions in the first coordinates, x is replaced by cos alpha, theta by beta, y by sine alpha, and theta by beta again. So we get cos alpha cos beta minus sine alpha sine beta. And for the second coordinates, we make the same substitutions. And we get cos alpha sine beta plus sine alpha cos beta. So now we've completed the problem. We know that r beta maps cos alpha sine alpha to the point with these coordinates. So let's collect our thoughts. The rotation r alpha plus beta takes 1 naught to cos alpha plus beta sine alpha plus beta. But if we look at it as two successive rotations, then we see that r alpha takes 1 naught to cos alpha sine alpha, and now we've seen that r beta takes that point to the point with these coordinates. But this point and this point must be the same, so the coordinates must be the same. So that means that the first term here must simply be cos of alpha plus beta, and the second term, well, that must just be sine of alpha plus beta. And that gives us the formulae that we're looking for. Cos of alpha plus beta is cos cos minus sine sine, sine of alpha plus beta, cos alpha sine beta plus sine alpha cos beta. And these are the fundamental formulae that allow you to expand sine alpha plus beta and cos alpha plus beta. And you'll find that you'll need these as part of your basic trigonometric toolkit as you go through the rest of the course. Well, so far we've been concerned with sines and cosines of angles, but there's another important trigonometric function that we haven't discussed yet, and that's the tangent. We'd like to use our geometric definition of the sine and cosine to give a geometric interpretation of tan as well.
Now, tan theta is defined as sine theta divided by cosine theta. And cosine theta and sine theta are the coordinates of this point. So tan theta is this length divided by this length. But what we want is a single length that is tan theta. Now, this side has length sine theta. So if we dilate by a factor of 1 over cosine theta, then we'll get a triangle which has a side of length 1 over cosine theta times sine theta, and that's tan theta. Well, where will a dilation of 1 over cosine theta take this triangle? Well, this side has length cosine theta. So when we dilate it by 1 over cosine theta, we get a side of length 1. So this vertex moves out to here, and the original triangle, which had a right angle here, dilates to this triangle. And I claim that this point here has coordinates 1 tan theta. Well, let's just check that. How do we get this vertex? We get it by dilating this vertex of the original triangle by a factor of 1 over cosine theta. And so the dilated point has coordinates 1 over cosine theta times cosine theta, 1 over cosine theta times sine theta. And that is 1 tan theta. So the y-coordinate is tan theta, and it's this length, and it's cut off by the angle theta along this line. And that line's a tangent to the circle. And in fact, that's where the trigonometric tangent gets its name from. So let's now use this picture of tan theta to explore some of its values. So, to find tan theta, we start from cosine theta and sine theta and dilate by a factor of 1 over cosine theta. So cosine theta sine theta dilates to 1 tan theta. So tan theta is the y-coordinate of a point on the tangent to the circle through 1, 0. When theta equals 0, tan theta equals 0. And tan theta increases as theta increases. When theta equals pi over 2, the lines don't intersect, they're parallel. So tan pi over 2 doesn't seem to exist. If we look at the definition of tan theta, it's sine theta over cosine theta. And cosine of pi over 2 is 0. So tan pi over 2 is not defined when theta equals pi over 2. What happens if we increase theta beyond pi over 2? What's tan theta now? Well, we still divide by cosine theta to get a point whose coordinates are 1 tan theta. And that point with x-coordinate 1 must lie on this line. Now we're dilating by 1 over cosine theta, which in this quadrant is negative. So we have a negative scale factor, which explains why we end up down here. And that's what we would expect, as tan theta is negative for theta in the second quadrant. So once again, we join the point and the origin, and we see where that line intersects the tangent to the circle. So for theta in this quadrant, we can find tan theta by extending the radius backwards so that it intersects the tangent again. Now we can continue plotting tan theta for theta up to pi. When theta equals pi, tan theta equals 0. Now what happens for theta greater than pi? We dilate by 1 over cosine theta. Remember, cosine theta is negative in this quadrant. Once again, we get 1 tan theta as a point on the tangent. When theta is in the fourth quadrant, that's just like the first quadrant. We extend the radius directly to the tangent.
So sine, cosine, and tangent can all be defined by lengths on this diagram. Now we've already used this picture to plot graphs of sine and cosine, so to finish the program, let's plot the graph of tangent. We want to plot this length along the tangent. Rotating anticlockwise gives the graph for positive theta. And for negative theta, we rotate the opposite way. We've drawn a small section of the graph for tan theta, and the graph continues repeating itself indefinitely in both directions.